Okay, so this problem is asking about electric flux, and this is using Gauss's law. So, and they're saying that I have a surface, say something like that, and it's going to be rotated, and it's in an electric field. So let's say the electric field is pointing this way. And what Gauss's law says is that if you have a field going through an area, that you can calculate what the charge is. And so the Gauss's law says that E times A is equal to Q over epsilon naught. But they're asking about the flux. So flux means how much electric field through an area. So flux is equal to just E times A. And so that's equal to 6.2 times 10 to the 5th newtons per coulomb times 3.2 meters squared. And so when I multiply that out, I get 1.984 times 10 to the 6th Newton meter squared per coulomb squared. And so that agrees here with that A. And so then it says, what about when the electric field is parallel to the surface? And here the answer is 0, because when this turns, the electric field needs to go through a surface. And when it turns and the electric field is parallel to it, the electric field isn't going through the surface. It's parallel to. So we end up with that B, that the answer is 0. Okay, for the next problem, it's saying that the electric field everywhere on the surface of a charged sphere is of radius blank has a magnitude of 575 newtons per coulomb and points radially outward from the center of the sphere. So outward is important. It tells us the charge, whether it's positive or negative. And it says, what is the net charge on the sphere? So again, we can use Gauss's law. And so Gauss's law says E times A is equal to Q over epsilon naught. And so we're trying to find Q. So Q is going to equal epsilon naught times E times A. And when I multiply that out, I get 8.85 times 10 to the minus 12. I'm not going to include the units, but you should. I just forgot them at this. I think it's coulomb meter squared, no, coulomb per Newton meter squared, something like that. I think it's coulomb squared, yeah. Okay, and our E is 575 newtons per coulomb, and our, so here we're told the sphere, so remember the surface area of a sphere, so we'll call SA of a sphere, is equal to 4 pi r squared. So I'm going to put 4 times pi, and then times 0.23 meters squared. And so when I multiply that out, I get, let's say this is equal to 0.38 times 10 to the minus 9 coulombs. And you can see my units here. I'm going to end up with a coulomb cancels with 1 coulomb here, so I still have a coulomb. My newtons cancel here. I'm going to have meters squared here, and they're going to cancel. So I'm just left with a coulomb, so that makes sense. It says, what can you conclude about the nature and distribution of charge inside the sphere? Well, I'm assuming that this is a spherical shell, meaning that it's hollow. And so since there's nothing on the inside, that if it's a shell, then on the inside the charge would be 0, as would the field. But in terms of, if I think about this sphere, it's going to be it's positively charged because the field lines point away from the sphere. So we know that it's positive. Okay, this problem was kind of tough to read, but I'm guessing based on the answers that this this outline right here is S2, and I'm guessing that that this right here, that's a negative 2Q. and I'm assuming that that this is a negative, let's see, yeah, that this is a negative Q, and this is a negative Q. And does that, with that, or and one of them has to be positive. So, well, anyway, we know that S2 has to be 0 because there's nothing inside of here. So there's no charges, right? We're going to use Gauss's law. EA is equal to Q over epsilon naught. So we want to look at this formula that we need our Q. So if I F S2, there's no charge inside, so my E2 is going to be equal to 0. So our phi is flux, so EA for surface 2 is going to be 0. And now for one of these charges, I'm going to be balancing so I'm going to have a negative 2Q here, and then a positive Q here, possibly. And so that would give me, when I add up the charges, negative 2Q plus positive Q would give me a negative Q. So that's going to be this one. Then I have one that is, I have a negative, I have a negative Q here and a negative Q here, possibly. So that would give me a negative 2Q. So adding them up, negative, negative. And then last but not least, I have this S4. So what you want to do is add up the charges that are within this area, and that will tell you what the flux is. So this would be the flux EA. So I'm looking for to say how many charges are within the surface, and so I just add them up and put them over epsilon naught, and that's going to be my flux.